What did you do today? Good question. Well, many of you had a midterm yesterday. Some of you have a midterm on Friday, right? Right. Maybe some of you, maybe none of you have a midterm on Friday here. Um, Gosh, what to talk about? You've got some ideas, but so there's one thing I feel like I should talk about, but it's kind of weird. So I feel like some of your instructors might have talked about how to find the derivative of inverse functions. See, a few had not. Okay, we'll talk about this briefly. It's kind of funky, but it works once you have seen how it works. So let's look at this example. We're going to graph the function f of x equal to x cubed minus 1. And without, x cubed plus 1, apologies. And without finding it, even though we will find it eventually, we're also going to graph the inverse function, which we can definitely find, just we won't do it yet. So this is your usual cubic function, just shifted up by 1. So I usually think of graphing the points like -1, -1, 0, 0, and 1, 1, and maybe like 2, 8. I'm just going to shift all those up by 1 y value. So I'm thinking of graphing if x is 0, y is 1. If x is 1, f of 1 is 2. And if x is 2, f of 2 is 8, which, okay, it's a little ways up there. And then if x is -1, I get 0. If x is -2, I get -7. So like maybe down here-ish. It's not perfect, it just kind of looks about right. Flattens out right there for a second, continues onward. Let's go ahead and label these points. This is 2, 9. That's 1, 2, 0, 1, -1, 0. And I guess, sure, -2, -7. To graph the inverse without actually finding the inverse, all we have to do is interchange all of the x and y coordinates. So every pair of points, I'm going to flip them and get the opposite pair. So instead of -1, 0, I'm going to get 0, -1. Instead of 0, 1, I'm going to get 1, 0. Instead of 1, 2, I'm going to get 2, 1. Instead of 2, 9, I'm going to get 9, 2. That make it look about right. I said 2, 1, but I feel like I graphed 2, 2. Sorry about that. That red point's a little too high there. Apologies. And then finally over here, 9, 2. So it's going to look kind of like this. And it kind of comes down like that. And then we also get -7, -2 over here. So maybe not quite perfect, but close enough. And again, ignore that red dot right there. That is not the right point. Sorry about that. So here's our f inverse of x. And here's our f of x. And so what I'm really interested in here is how does the slope of f of x at x equal to 2 compare to the slope of f inverse of x at x equal to 9. Over here, right there. I'm interested in the slope here and the slope there. Well, let's go ahead and find the inverse function so we can answer this question. Because again, when we talk about slope of a function or slope of the tangent line of a function, we really are just talking about the derivative. So let's go ahead and find f inverse. We can do the usual thing to find the inverse function. We're going to write y equal to x cubed plus 1. We're going to switch x and y. By the way, if I stopped right there, although it's not the function, this is the thing I graphed, right? If you plug x equal to y cubed plus 1 into Desmos, it'll give you exactly this red graph because you've got the right relationship at this point. But we're going to solve for y. So we're going to subtract 1 from both sides. X minus 1 equals y cubed. And then take the cube root of both sides. So we're going to get the cube root of x minus 1 equal to y. Or if you prefer, f inverse of x equal to the cube root of x minus 1. So there's an inverse function. And now what I really want to know about is how do their derivatives look at these points I'm talking about? So let's go ahead and find the derivative of f. So f prime of x is equal to 3x squared. And if I want to find the slope of the tangent line to f at x equal to 2, I'm just going to plug in the 2. So I'm going to say that f prime of 2 is equal to 3 times 2 squared, which is 3 times 4, which is 12. Okay, let's look at the other thing. So let's look at f inverse. And yeah, I'll write this the following way. So f inverse of x, if I'm going to take a derivative, I'd rather write that root as a fractional power. So let's say that f inverse of x is x minus 1 to the 1/3 power. And then our derivative is going to be, so this notation gets kind of funky. I'm going to write the following, the derivative of f inverse with respect to x. So df inverse dx, just to make the notation, like it's weird writing f inverse prime of x, it just looks kind of funky. So we're going to take the derivative just using the regular rules. So I got some stuff to the 1/3 power. My derivative is 1/3 times that stuff. To the 1/3 minus 1 is negative 2/3. And then we would multiply by the derivative of the inside stuff, and the derivative of the inside stuff is 1. And now we're going to plug in the point I asked about, which is the point x equal to 9. So if I take my derivative of my inverse function and plug in x equal to 9, I'm going to get 1/3 times 9 minus 1 to the negative 2/3 power. Okay, that's going to be 1/3 times 9 minus 1 is 8. If I bring this 8 down to the denominator, it's not raised to the negative 2/3, it's raised to the positive 2/3. And then whenever I'm doing that 3 looks terrible. Sorry about that. Whenever I'm doing a fractional power like that, I always do like the denominator part first. So 8 to the 1/3 is the cube root of 8, which is 2. And then 2 squared is 4. And then 3 times 4 is 12. So this is 1/3 times 4, which is 1/12. And it is not a coincidence that the slope of this original f of x was 12 and the slope of the derivative of the slope of the inverse function was 1/12. That is actually by design. Because if you think about it, if these functions are reflections of each other across the line y equals x, well here you're going, your tangent line, you're going over a little bit and up a lot. And since you're kind of inverting the relationship, now over here at 9, 2, drop pens everywhere, you're going over a lot and up a little bit. And those slopes are exactly reciprocals of each other or inverses of each other. So this leads to the inverse derivative theorem, which kind of technical, but I'll just say what it is. So here's the idea. So this result from above suggests the following theorem. And I should say the theorem about, sorry, there's more words to say there, about the slope of an inverse function. So if we want to find the derivative of f inverse evaluated at some point b, then that's going to be the same as finding the inverse or reciprocal of the derivative of the original function, f prime, but the thing we're going to input isn't the same, right? If we think about looking back at this example over here, in the inverse function, we were trying to plug in 9. So if we think of like this as b and this as f inverse of b, well, then the thing we want to plug into the f function was the 2 part, which is the f inverse part. So we actually want to say not f prime of b, but f prime of f inverse of b, the corresponding value on the other function. And that's kind of it. Another way of writing this, alternatively written as the derivative of f inverse with respect to x evaluated at x equal to b is equal to 1 over the derivative of f of x evaluated at x equal to f inverse of b. It's literally the same thing, just written a different way. So kind of weird, but also kind of useful. There's 2 uses I can think of for it. So sometimes people do like to ask questions like this, meaning someone could ask us the following sort of question. Find the slope of the line tangent to the inverse of the function f of x equal to x to the 5th plus x cubed plus x at the point 3, 1. Okay, so one reason we might need this theorem is because we can't do this the way we did the other one. We can't actually find the inverse function here, right? If I do y equals x to the 5th plus x cubed plus x, and then switch x and y and try to solve for y, I'm not going to get there. It's really probably super extremely challenging to solve for y. It might be even impossible, or it might require methods that I've never heard of. But the idea here is to use the inverse function theorem, the inverse derivative theorem. I think that's what it's called. I don't think it really has a good name, to be honest, but this is what we're talking about here. So we're trying to find the derivative of f inverse at x equal to, this is the part that I always struggle with, to be honest. I'm really like, I have to think about this part every time, what I'm going to plug in. And so I'm actually not going to write anything down just yet. I'm going to go back and say, well, I know that means I want to find 1 over the derivative of f of x evaluated at x equal to f inverse of whatever. So if I know the point 3, 1, well, I wasn't super clear with what I said. Is 3, 1 a point on my function or a point on my inverse function? Well, let's check. If I plug in 3 for x, do I get 1 out? I don't, right? I get 3 to the 5th plus 3. Well, that's a big number. It's not 1. But if you switch it, if I plug in 1 for x here, do I get 3 out? And I do. So I'm thinking of this function, right? So essentially what I'm saying is we know that f of 1 is equal to 3 and f inverse of 3 is equal to 1. So 3 comma 1 is a point on the inverse function. So I'm trying to find the derivative of the inverse at x equal to 3, meaning I'm trying to find 1 over the derivative of the original function at x equal to f inverse of 3, which is x equal to 1. So what we're going to do is we're going to find the derivative of this function, which should be not terrible at all, right? It's a nice, easy thing to differentiate. And then we're going to plug in 1 for x. So this is going to end up equaling 1 over, here our derivative is going to be 5x to the 4th plus 3x squared plus 1. And then we're going to evaluate that at x equal to 1. So we're going to get 1 over 5 times 1 to the 4th is 5, plus 3 times 1 squared is 3, plus 1, that's going to be 1 over 9. Let's take a look. Because I think we can see this on Desmos, and I think it might be kind of cool. It might not be cool, it might be kind of boring, but who knows? I mean, here's the truth. I think it'll be kind of cool. You all might think it's kind of cool, but you might not. So here's the original function. It was y equal to x to the 5th plus x cubed plus 1, right? No, plus x, sorry. And if you notice here that at the point of tangency, which is 1 comma 3, the slope of the tangent line is going to be 9. It's going to be y minus 3 equals 9 times x minus 1. Look at that tangent line right there. Definitely with a slope of 9. And now we can find the inverse function. Literally, we don't have to actually find the inverse function. We can just graph it by switching x and y. So I'm going to graph x equal to y to the 5th plus, plus James, not equals, plus y cubed plus y. That's kind of cool. It just gives us the inverse function just like that. And then we can see that at the point 3 comma 1, the tangent line is aligned with a slope of 1 over 9. We get y minus 1 equal to 1/9 times x minus 3. It's kind of cool. So really, these inverse functions at corresponding points where you've interchanged x and y, the slopes have to be reciprocals of each other, because the change in y over the change in x flips and becomes the change in x over the change in y. Kind of neat. I think it's really neat, actually. I'll be honest, I used to hate this theorem a lot. It really kind of made me, I don't know, just angry because there was something about it I just didn't like, but I've grown to like it over the years. So let me have you all try one on your own. So let's say this is our function. Our function is f of x equal to e to the negative x squared plus x. And we want to find the derivative of the inverse function evaluated at x equal to 1. Now, I didn't tell you the y coordinate there with a purpose. So what you're going to have to find is 1 over the derivative of this function over f prime of x. And you're going to have to plug in x equal to f inverse of 1. Or in other words, to figure out to figure out what you need to plug in here, you're really asking the question, f of what number is equal to 1? That's going to give you f inverse of 1. Now, I'll give you a hint. I'm not going to tell you, but I'll give you a big hint. There's only really one number you can plug into e to the something and get a nice integer result. Don't say it. Just keep it to yourself. E to the some power is a nice number. E to any other power is not so nice. Okay, give it a try. You might start just by finding the derivative. So find f prime of x first to plug in there. Question. Oh, sure. So our derivative should look like, well, I've got e to the stuff plus x. The derivative of e to the stuff is e to the stuff times the derivative of that stuff plus the derivative of x is 1. So this is going to end up being e to the negative x squared times negative 2x plus 1. So now we have to figure out what we're going to plug in. So this is going to equal, sorry, I got a lot of arrows here right now. So we're going to getting that the whole thing is equal to 1 over e to the negative x squared times negative 2x plus 1, evaluated at x equal to what? What can we plug in for x here and get 1 as our result? It's got to be 0. And if you see e to the something, you usually want to end up having e to the 0. So the e to the 0 ends up equaling 1. This is the only nice value you're ever going to get out, really. So here, you can see that, oh yeah, f of 0 is equal to 1 because it's e to the 0 plus 0. That means f inverse of 1 is equal to 0. So that means we have to plug in x equal to 0 here. So if we do that, we're going to get 1 over e to the 0 times negative 2 times 0 plus 1, which is going to be 1 over 1, which is 1. Which might not be super exciting because the derivative of the original function would also be 1, but that's the idea here. Okay, there's one other thing to say about this kind of stuff, and then we'll move on to other things. But I'll say there is a derivative that not all your instructors might have shown you, but definitely when you take 17B, everyone is going to expect that you know whether or not you've seen it in 17A. So let's talk about that function next. So we're going to talk about some inverse trig functions and their derivatives. So we'll start off with tangents. So we're going to graph first y equal to tangent of x. And we're just going to do kind of a very easy graph of it. We know that tangent has some vertical asymptotes at pi over 2 and at 3 pi over 2 and every odd multiple of pi over 2, also at negative pi over 2 and negative 3 pi over 2 and so on. And then the graph of tangent looks something like this. So it goes to the origin and kind of does this deal here. And then it just repeats itself. Just like any trigonometric function, right? After you get one period of it, for tangent, the period is a length of pi, not 2 pi. And after you get one full period, it just repeats the same thing over and over and over again. Now, I know it's been a little while since we talked about inverse functions, but I will remind you that this function on its own, without anything done to it, is not invertible. This function fails the horizontal line test. It's not one-to-one. If you interchange x and y, if you graph x equal tangent of y, it looks like a bunch of tangent graphs turns on their side, and it really, really, really fails the vertical line test. Let me show you what this thing looks like, just because I think it's kind of neat to see. So if we look at y equals tangent for a second, just so you can see a nice perfect graph of it, there's y equals tangent of x, lovely. Got the vertical asymptotes where we said they were. But now if you switch things around and you graph x equal to tangent of y, and we turn this one off, not a function. Fails the vertical line test, right? Each x input has multiple outputs associated to it. And so the thing we have to do to make this inverse function or inverse relationship into a function is you have to restrict the original function. So what we're going to do is we're going to take this original function and say, well, we're going to restrict x to be being between negative pi over 2. Sorry, I forgot a brace here. and pi over 2. So we're just going to have one period's worth of tangent, and then we're going to invert that. So here's what we get. We're going to take just this section here, and we're going to take the inverse of that to get f of x equal to the inverse tangent of x, or as many people like to write it, myself included, f of x equal to the arc tangent of x. So the same name, same function, just a different name for the same function. So the graph of this is going to look like we took this middle section here and inverted it, reflected it across the line y equals x. So instead of getting vertical asymptotes at x equal to pi over 2 and x equal to negative pi over 2, we're going to get horizontal asymptotes at y equal to pi over 2 and y equal to negative pi over 2. And then this graph is going to look like this. And since we're here, we might as well say the domain of this function is all real numbers, everything from negative infinity to infinity. The range of this function is negative pi over 2 exclusive to positive pi over 2 exclusive. And then we could ask questions like, what's the inverse tangent of 1? What's the angle? So when I see this notation, inverse tangent of 1, I'm really thinking, okay, this says what's the angle whose tangent is equal to 1? Inverse tangent of 1 is exactly pi over 4, because tangent of pi over 4 is equal to 1. I just want to be extra super clear here. When we talk about this, there are lots of other angles you can take tangent of and get 1. Like if you go a whole period away, 5 pi over 4, tangent of 5 pi over 4 is also 1. Or 9 pi over 4, or 13 pi over 4, or any odd multiple of pi, well, every other odd multiple of pi plus something over 4, that's going to give you tangent to 1. But this is the only angle we say the inverse tangent of 1 is equal to, because when we want the inverse tangent to be a function. To be a function, each input has to have only one output. If I wanted to find the inverse tangent of, say, the square root of 3, which is hard for me to think, oh, the negative square root of 3, well, I'm trying to say, well, what angle is that equal to? I'm not sure, but I know that it's supposed to mean that tangent of that angle is equal to negative root 3. So I'd probably draw a triangle. Say, okay, well, I know that in my triangle, tangent should be opposite over adjacent. So it's going to be something like the opposite side being negative root 3, the adjacent side being 1, and this side being 2. That angle there, this looks like my usual 30, 60, 90 triangle. I know, again, it's been a while since we talked about trigonometry at all, but in a 30, 60, 90 triangle, the short side opposite the 30-degree angle is 1, the long side opposite the 90-degree angle is 2, and the medium side opposite the 60-degree angle is root 3. So it looks like tangent of 60 degrees is equal to root 3 over 1. So tangent of 60 degrees, which is pi over 3, would be equal to root 3, but I wanted negative root 3. So instead of going counterclockwise and getting a positive angle, we're going to measure it clockwise and get a negative angle. So our angle here is going to be theta equal to negative pi over 3. Most of this is just to point out what the inverse tangent function really is, right? It's the function that if you are telling me what the value of tangent is equal to, it gives you back the angle that you plugged in. Okay. But now for the part that's actually kind of now for the part that you're going to be expected to know about when you take 17P. So there's some alarm going off, right? I'm not crazy. Like you guys hear that? Okay. Yeah, there's something going off. Oh well. So what we really want to be able to do here is to find the derivative of inverse tangent of x. And I'm going to show this to you. Yeah, I'm going to show it to you in two different ways. So here's one way. Here's the way using the theorem we just talked about. No, maybe, you know what? Why be crazy? I'm going to show you to the way you should know it, not the way using that theorem, because the theorem, it seems funky to me. So here's what I would actually do. We're trying to find this derivative, so we're going to set y equal to the inverse tangent of x. And this is going to feel very similar to how we found the derivative of the natural log of x by rearranging the equation and differentiating both sides implicitly. So we know that if y equals inverse tangent of x, it's like y is our angle and x is our value. That's equivalent to saying tangent of y is equal to x. These mean the same thing, right? Again, kind of like just before we were saying, oh yeah, tangent of pi over 4 equals 1, inverse tangent of 1 equals pi over 4. You can think of this as your x and this as your y. That's your y, that's your x. And now we're going to take the derivative of both sides of this equation. The derivative tangent of y, well, the derivative tangent of something is secant squared of that something. But then, because of the chain rule, we have to multiply by the derivative of the inside thing, which is dy dx. On the other side, the derivative of x is 1. And then, just like every other time we've used implicit differentiation, we're going to solve for dy dx. So we're going to get dy dx equal to 1 over secant squared of y. But then, like the times we found the derivative of natural log of x, if we started off with a function of x, we should be able to end with a function of just x. So we're going to plug back in what secant squared of y is. What is secant squared of y equal to? There's a couple ways to do this. One way, which is my preferred way, is to draw a triangle. So looking back here for a moment, if I'm saying that tangent of y is equal to x, I can only think of that as tangent of y is equal to x over 1, the opposite over the adjacent. So now I'm going to draw a triangle where y is my angle, the opposite is x, the adjacent is 1, and we're going to use the Pythagorean theorem to find that missing side. So this third side here is, we don't know, but we know that 1 squared plus x squared should equal the missing side squared. And then if we take the square root of both sides, the missing side is going to be the square root of 1 squared is just 1 plus x squared. Now, technically, I've overlooked something. When you square root both sides, we often get a plus or minus. We don't really need to worry about it, but I will address it in a moment. So here's what we're going to end up getting. We're going to end up getting the dy dx. Oh, let's see. So I want to find secant squared of my angle. I never remember what secant is. I know that cosine is the reciprocal of secant. I know that cosine of y is the adjacent over the hypotenuse, which in this case is going to be 1 over the square root of 1 plus x squared. Right? Yeah, that's right. So then secant of y is the reciprocal of cosine. It's going to be the square root of 1 plus x squared. So then secant squared of y should be 1 over the square root of 1 plus x squared, which is just 1 over 1 plus x squared. And the reason here we didn't have to worry about the plus or minus is because if there's a plus or minus there, well, if you square it, it's going to get rid of the plus or minus anyway. A positive thing squared is positive, a negative thing squared is positive. So either way you slice it, the derivative of the inverse tangent of x is equal to 1 over 1 plus x squared. As a side note, I will just mention, instead of doing this whole triangle thing, which I like to do, I think it's kind of neat, you could have also used a trig identity. One of my favorite trig identities, which I think I've said in this class, but I don't know if I have, is, well, here's the most famous one, which we have talked about, cosine squared of y plus sine squared of y equals 1. But then there's another one, which I feel like I must have said. It's I tan and get sexy. 1 plus tangent squared y equals secant squared y. I tan and get sexy. A student told me this one time. I clearly have it was probably like 15 years ago at this point. I have never forgotten it. It's unforgettable. I tan and get sexy. 1 plus tangent squared of your angle equals secant squared of your angle. So that means, oh, look, we can replace the secant squared of y with 1 plus tangent squared of y, but tangent of y is equal to x. So what we really have is 1 plus x squared equals secant squared of y. And then we just replace the secant squared of y with 1 plus x squared, giving you the same result. So, to make a long story much shorter, definitely when you take 17b, there will be a time where you're expected to know that the derivative inverse tangent is equal to 1 over 1 plus x squared, or more importantly, the antiderivative of 1 over 1 plus x squared is equal to the inverse tangent of x function. That's where this comes up, actually. As far as this class is concerned, if your teacher hasn't taught this to you, you probably won't have to worry about it, but it definitely does come up in 17b. So don't forget about it, or remember it when it comes up. There are other inverse trig functions we could find derivatives of, but it never gets taught in the 17 series for whatever reason. So although we could try to figure out what the derivative of the inverse sine function is, or the inverse cosine function, I don't think it's worth our time because I don't think it's going to come up for you at all. That said, if it does, right, if your teacher starts talking about the derivative of the inverse sine function, let me know. We can definitely cover it. I just don't want to waste your time. Any questions about any of this before we move on to something a little bit different? Okay. Where are we at? Let's see. Let's talk about, I think this is section 3.8, linear approximations. The idea behind a linear approximation is that for some functions, we can use a straight line to get a value for them that's close to the value we're interested in. Like the following example. We're going to use a linear approximation, which we'll explain as we go here, to the function f of x equal to the square root of x, which is definitely not a linear function, right? It's not a straight line. That function is curved at a equal to 25 to help us estimate the square root of 27. And I'll point out, right, the square root of 27 is not something that I know right off the top of my head. I'm pretty sure, though, it's a little bit bigger than 5. Because I know the square root of 25 is 5, and the square root of 27 should be bigger than that. So let's draw ourselves the picture here. So we're going to draw the square root function. Something like that. Maybe it's a little bit exaggerated there. So here's our f of x equal to the square root of x. And we're really interested in looking at the tangent line to this function at the nice value that they've given us. So at a equal to 25, it's right there, we're going to draw the tangent line. Let's draw it. Pen, maybe not. Where'd you go, red pen? I always lose my red pen. There it is, right over there. So there's our tangent line. And the idea here is that after we find the equation of this tangent line, instead of plugging in 27 to our original function, which is hard to calculate the square root of 27, we're going to plug in 27 to our linear function, where it's easier to figure out a line with 27 plugged in as the value to end up getting our approximation. So we're going to say that this value here, which we're going to call capital L of 27, capital L for linearization, that's going to be a pretty good approximation of f of 27, which is the square root of 27. That's the whole idea here, is that as long as you aren't too far away from the point of tangency, you can use the straight line or the linearization to approximate the function value. Let's go ahead and do it. So we're going to start by finding the equation of the tangent line. To f of x equals the square root of x at x equal to 25. So cool, that's not that hard to do. We've done equations of lines before. We know that the general way we find the equation of a line is going to be y minus the y coordinate equal to our slope times x minus the x coordinates. Now, for whatever reason, people like to write this a different way. So instead of writing it like this, what we're actually going to do is we're going to isolate y. We're going to write it as y equal to y naught plus our slope times x minus x naught. And instead of using x naught, we're going to use a instead of x naught. We're going to use f of a instead of y naught. And we're going to use for our slope the derivative f prime of a. So the way we usually write this linearization of our function at the point, which again, linearization just means the equation of the tangent line. We often rewrite this as L of x equal to f of a plus f prime of a times x minus a. That is the typical notation for this. But then we can find all the things. So let's find all the things. So if our a value is 25, our f of a is going to be the square root of 25, which is 5. And to find the slope, I first have to find the derivative. So my function was the square root of x, or x to the 1/2 power. My derivative is going to be f prime of x equal to 1/2 times x to the negative 1/2. And then when I plug in a, my f prime of a is going to be 1/2 times 25 to the negative 1/2 power. Okay. Question for everybody. What's 25 to the positive 1/2 power? Show me on your fingers. This many. 25 to the 1/2 power is the square root of 25, which is 5. Okay, so if 25 to the 1/2 is 5, 25 to the negative 1/2 power should be the reciprocal of that. 1/5, 1/5. So this 25 to the negative 1/2 is really the same as 1/25 to the positive 1/2, which is 1/5. And then 1/2 times 1/5 is 1/10. So here's what my linearization equation looks like. L of x, the equation of this tangent line, is equal to f of a, which is 5, plus f prime of a, which is the slope, which is 1/10, times x minus a, and a was 25. Now check this out. If we plugged in 25 for x, we'd get exactly 5 back. Because if we plug in the point that we're doing the tangent line at, we should get exactly the right value. But the idea here is that we're going to move away from that. So we're not going to plug in 25 for x, we're going to plug in 27 and say that, okay, the square root of 27 is approximately our linearization evaluated at 27. See over here how they're not the same? right? Square root of 27 and L27 are a little bit different than each other. But then we're just going to plug in 27 to our formula here, and look how easy it is to calculate this. This is 5 plus 1/10 times 27 minus 25. 27 minus 25 is 2. 2 over 10, you can either write it as a fraction, 1/5, or as a decimal, 0.2. This is 5 plus 0.2, which is 5.2. Which seems reasonable, right? We expected the square root of 27 to be a little bit bigger than the square root of 25, which is 5. The question I always like to answer is, how good was our estimate? Well, if we take a calculator and actually calculate the square root of 27, sometimes these calculators kill me. So yeah, yes, I'm aware of that. I wanted the decimal approximation, which I never really know how to find. There's a button on here that's supposed to do it. You're really not helping me out, calculator. Where'd you go? There is a button that does the thing I'm looking for. I don't remember what it is. This calculator is too fancy for me.
It's about 5.
So about 5.19. Thank you. I appreciate it. So actually, approximately 5.19. So our estimate was pretty good, right? Without doing any sort of hard math, really, right? We didn't do anything that crazy. We found the equation of a tangent line. We plugged in a point. We found a decent estimate of the square root of 27. So that's the whole idea with linear approximations and linearizations, is we can use these tangent lines to approximate a function evaluated at some more challenging value. And we'll mention, if you're taking 17C, this idea does come back, where you're linearizing a function, except the idea in 17C is that you're linearizing two functions at once. And it's a function of two variables, not one variable. So, but it's really, the equation looks very, very, very similar to this here. You're just like adding on another piece. So this idea will, and again, not everyone has to take 17C, but if you have to take 17C, you'll see this idea again. Especially if you come to the code class for 17C. Like, oh yeah, remember we talked about linearizations? Okay. Let's look at a couple more examples, because sometimes things can be a little bit more interesting. Yeah, let's look at that. So sometimes the question can be very kind of directive, like telling you to do all these things. Sometimes it can be as simple as saying something like estimate 1.97 to the 5th power. I feel like that's not quite enough. I should say by using a linearization. Now, unlike the previous example, they haven't told us what the function is. Right? The previous example, they're like, oh yeah, the function square root of x. And they said linearize the square root of x at this point to get the equation of the tangent line and then plug in the nearby value to get the estimation. Here they've given us none of that. So we have to figure out what those things are. Fortunately, it's not too terrible to do so. So what I usually think about if I'm trying to think about what the function is basically if you see some number input into being raised to a power, or taking the square root of, which is still being raised to a power, or taking the sign, or basically if you're doing a function to a number, replace that number with x, and that's your function. So I'm thinking, okay, my function f of x, instead of being 1.97 to the 5th, is x to the 5th. I should also say, technically you could say, James, why not write it as like 1.97 to the x? Well, my answer to that would be because 1.97 is not a very nice number. So if you see a not nice number inside the function, that's the one you should replace. I will point out, although it'd be kind of weird, if someone said your function was something like, I don't know, 2 to the 4.03, then yeah, you might want to write your function as 2 to the x. And maybe we'll explore that one, although it's probably not very nice, so we probably won't. But yes, whichever number looks gross, that's the one you should be replacing with the x. Or more generally, whichever one is inside of the function. Come on, papers, stay together. Throwing things around here. Okay, fine, don't stay together. So there's our function, and then we also have to identify the nice point that we're actually going to plug into our function. So in this example, I want you all to think about or write down what you think the A value should be. The number that's close to the gross number we replaced, that's easy to plug in. Think about the number. I want you all to think about it on your own for a second and try to pick the nice integer number that is close to the thing we would want to plug in, but is not actually that number. What's the closest integer to 1.97? That many. Yeah, this many. 2. So our A value is 2. Your A is almost always the closest nice number. The closest number that is easy to plug in and calculate what that's going to be. Just like in the previous example, I was trying to calculate the square root of 27, and the closest nice number was 25 to plug in. All right, and then we have to find a couple other things. We're going to need the derivative. So we know that our derivative here is f prime of x is equal to 5x to the 4th. And then I like to write down the linearization formula because sometimes I forget exactly what I'm doing. So I know it's going to be that the linearization is equal to f of a plus f prime of a times x minus a. Again, just as a reminder, this is really just like y equals y naught plus m times x minus x naught, or y minus y naught equals m times x minus x naught. It's really just coming from your point slope form of your equation of your tangent line. But we write it like this because we do. So I guess I should find f of a and f prime of a. So f of a is f of 2, which is 2 to the 5th, which is 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. And f prime of a is 5 times 2 to the 4th, which is 5 times 16. And if you don't like doing 5 times something, you can multiply by 10 and divide by 2. So 16 times 10 is 160, divided by 2 is 80. Or you can divide by 2 and then multiply by 10. 16 divided by 2 is 80. 8, and 8 times 10 is 80. So writing my linearization, which is again just the equation of the tangent line, our linearization here is going to be f of a, which was 32, plus f prime of a, which is 80, times x minus 2. X minus a. That's our linear. So oftentimes with these kinds of questions, sometimes we ask 2 different questions. They ask first, find the linearization. And if they just ask for that, this is the linearization. The linearization of f of x equal to x to the 5th at a equal to 2. And then to find our approximation, to estimate 1.97 to the 5th power, which is f of 1.97, it's going to be approximately L of 1.97. And then we're just going to plug in 1.97 and get, oh, I know what I was going to say. So you might be tempted to simplify that line, right? You could totally multiply the 80 through and write it as 80 times x plus 32 minus 160 and combine that down to something. You shouldn't do that. It is almost never in your interest to simplify this down to be nicer, because the point is here is that when you plug in the number that we're actually trying to estimate the value of the function at, this part here becomes really small typically. And then usually this multiplication of a small number times that slope over there is easier to do than this bigger number times a small number than. So I would say, unless someone tells you otherwise, don't simplify this. Leave it as is and then just plug in this number to that. So it's going to be 32 plus 80 times 1.97 minus 2, which is then going to be 32 plus 80 times negative 0.03. And I know that 8 times 3 is 24. So 80 times 0.03 should be 2.4. If I multiply this by 10, it's 0.3. If I multiply it by 8 after that, it's 2.4. So I'm going to have 32 minus 2.4, which is going to be 29.6. Now I can use my calculator for this one without having to look for a silly button. And if we get that, if we actually plug in 1.97 to the fifth, we get 29.67 approximately. So yeah, good estimate. Decent job. I think there's something else I want to put out here. Maybe not. Okay. I think if there's anything else I want to say about this, really. Sure, let's do one more and then we'll see where we're at. Because, well, I realized I forgot my plug for my laptop, so it might die, which isn't like, doesn't mean I have to stop teaching class, but kind of makes it hard to record anything. So we'll see how the battery life lasts here. So why don't you all try this one actually? I want you to use a linearization of f of x equal to the natural log of x at a equal to 1 to then estimate the natural log of 1.04. So you should start off by finding the things you need in f of a plus f prime of a times x minus a. You already know what a is, you know what your function is, so you can find f prime of a and then write out your linearization. Wait, everybody get a chance to sign this? I'm curious, is Jasmine here? Someone else, Jasmine, your name is on the thing. Totally fine. I just want to let you know because you always write down here. I'm like, oh, it's right up there. This one isn't too terrible. If we take the derivative of the natural log of x, we get 1 over x. If we plug in 1 for x, our slope is going to be f prime of 1, which is 1 over 1, which is 1. And kind of even less excitingly, our f of a value or our y value here is going to be f of 1, which is natural log of 1, which is 0. So our linearization here isn't super exciting, but it's still the right thing. The linearization is just 0 plus 1 times x minus 1. And here you don't really need to write the 0 or the 1 out in front here. So we can really just say our linearization is x minus 1, which, again, if you graph this, is the right thing. If you graph the natural log function, which definitely has an intercept at 1 comma 0, it looks like this. And it certainly has a tangent line that goes through the point 1, 0, and also to the point 0, negative 1 with a slope of 1. And so then we can say, well, we're trying to approximate the natural log of 1.04. That's going to be approximately L of 1.04, which is going to be 1.04 minus 1, which is just 0.04. Sometimes people talk about this more generally, so I'll just point out that it's true that the natural log of 1 plus a small number, how small, like probably less than a tenth, is approximately that small number. This comes up semi-often, actually. For reasons I don't really know why, actually, but it does. Yeah. People seem to care about this a lot. I'm not really sure why. Okay, so. Yeah, okay. There's, let me see here for a second. Something I want to check. So this idea is actually a small piece of a bigger idea that really doesn't show up again until 17C. You could use polynomials of higher degree to approximate these functions. So there's this theorem that says, well, instead of using a first degree approximation, which is what we just used, right? And it was our linearization was just our f of a plus f prime of a times x minus a. You can actually extend this to any degree you want. So let me just show you before you write any of this down. So your second degree approximation would be, I guess I'll use q of x for a quadratic. Although I'm going to use different relations. It's going to be f of a plus f prime of a times x minus a. Plus here's the next term. It's the second derivative evaluated today divided by 2 factorial times x minus a squared. In case just to make sure everyone's cool with what a factorial is, so when we write 2 exclamation point or any number exclamation point, we say 2 factorial. And what that means, well, let me actually show you a better example down here. I'll point out that 4 factorial just means 4 times 3 times 2 times 1. So whenever someone says this, it just means take that first number and multiply it by every integer until you get down to 1. So 3 factorial would be 3 times 2 times 1, which is 6. 2 factorial is 2 times 1, which is 2. 1 factorial is kind of unexciting. It's just 1. And just so you all know, even though it's kind of frustrating maybe, 0 factorial is defined, and it's defined to be equal to 1. It's kind of like how something to the 0th power is defined to be equal to 1 because it needs to be, so that some other rules work the way they need to work. The same idea is true here. 0 factorial needs to be 1 because really, if I wanted to, I could have written that this first term here is really f prime of a divided by 1 factorial. And this f of a is divided by 0 factorial. So I really do need that to be 1 so that the pattern still works. And then I bet you all could make a pretty good guess what the third degree polynomial that approximate this is going to be. I'm going to call it T3 of x. The T is for Taylor. It's the name of the person that came up with this idea of a Taylor polynomial that approximates a function. And it's just what we had before. And then I want you all to try writing what the next term should be, or at least thinking about what it should be. So we got f of a plus f prime of a times x minus a plus f double prime of a over 2 factorial times x minus a squared plus, I want you all to think about for a second what the next thing should be. All right, but you've all got a pretty good guess. It's going to be f triple prime of a over 3 factorial times x minus a cubed. And so on and so on and so on, right? The next term, the T4 would have all that plus the fourth derivative of a over 4 factorial times x minus a to the fourth, and so on and so on and so on. You don't really need to know this for now, but I want to tell you two things about it. Thing one, it's kind of neat. Like, it's actually really cool, and I'm going to show you in a second here, that you can actually use this to take a function that isn't a polynomial and then use polynomials to approximate, to look more and more like it. And the more terms you use, the closer your polynomial gets to actually looking like the actual function. And what was the other thing I wanted to say? I forgot what the other thing was. Sorry, there was something else. So let me show you one example of this, just to kind of, so let me show you one easy example of this. So we're going to find some Taylor polynomials. We're going to find the first, second, and third degree Taylor polynomials for f of x equal to e to the x. E to the x is kind of the best thing ever because it's its own derivative. So we know, oh, sorry, I need to tell you at a equal to 0. And then we'll see some neat pictures in a minute here. Oh, I know. So there is a really actually cool video about this idea, which I will post on Canvas. It's by 3 Blue, 1 Brown. If you ever watch, they make some really neat math videos. I'll post this here. It just kind of goes into more explanation about why and how this works. But it's just kind of a neat idea that functions that are not polynomials can sometimes actually be represented by an infinite polynomial added together. Kind of weird. So let's see. Nice thing here is that all my derivatives are going to be e to the x. The first derivative is e to the x, the second derivative is e to the x, the third derivative is e to the x, and so on and so on. And then I know that my f of a, which is going to be f of 0, is e to the 0. And actually, so is every derivative, right? F prime of a is going to be f prime of 0, which is still e to the 0, which is 1, which is 1. So every derivative is going to equal 1. So then using these formulas, my linearization, also known as my first degree Taylor polynomial, is just going to be my f of a plus my f prime of a times x minus a. Okay, not super exciting yet. It's 1 plus x. Well, let's look at the second degree one. My second degree Taylor polynomial is going to be 1 plus x plus 1 over 2 factorial times x minus a squared. Since a is 0, I'm not going to write x minus a. And now my third degree is going to be 1 plus x plus 1 over 2 factorial times x squared plus 1 over 3 factorial times x cubed. And I know you're going to go, but hold on just one sec. It's really neat. I just want to show you. I want to show you the picture because it's really, really cool. You're welcome to go, but hold on for just 1 second. So here's what's really cool about this. It actually does the thing we think it does, which means like if you graph e to the x, okay, fine. But then if you start graphing these approximations, well, not super exciting at first. Yeah, okay, it looks like it. But if you keep adding on terms, it gets closer and closer. So now that quadratic approximates it better for longer. And if you add on the next term, x to the third divided by 3 factorial, it does it for even longer. And the more terms you add on, the better and better it gets. Okay, you're free to go now. But I just wanted you to see that because I think it's really neat. Good, I'm glad. So if you do this literally forever, the polynomial actually is e to the x. I should say the Taylor polynomial is. So kind of cool. We don't really use it for a whole lot in this class, But when you get to 17C, this Taylor polynomial idea comes back, and we use it for something actually very necessary in 17C. So I wanted to at least expose you to it so you see. There's something else I want to say. No, I think that's it. So I think that's a good concluding point. Let's stop there. I know it's a little early, but I think we can stop there and my computer won't die and I can go get my plug. So have a good rest of your day.